Good evening and welcome. Welcome to the first Math Matters lecture for the 2006-07 season. I'm Douglas Arnold. I'm the director of the Institute for Mathematics and its Applications, the IMA, which brings this series to you. And so that means it's my privilege to introduce our speaker, Margaret Wright. Margaret Wright studied mathematics and computer science at Stanford University, got her PhD degree in computer science in 1976 at Stanford, stayed at Stanford as a researcher until she went to Bell Labs in 1988, where her career took off, and she has risen to be one of the world's authorities in the big area of optimization. In particular, she's recognized as a world authority on nonlinear optimization with constraints. She wrote a book on this, I guess, back in something like '81, which is still in print after 12 printings, a Bible in the field called Practical Optimization. In 2001, while she was at Bell Labs, Margaret rose through the ranks. She became what is called a distinguished member of the technical staff, a Bell Labs fellow, head of the Department of Scientific Computing Research. And then in 2001, she moved to the Courant Institute of Mathematical Sciences at New York University, where she's the Silver Professor of Computer Science and the head of the Computer Science Department. She's received almost all the research recognitions one could imagine. She's a fellow of the American Academy of Arts and Sciences, and a fellow of the National Academy of Engineering, and a fellow of the National Academy of Sciences. Very rare. In addition to her research, Margaret is extremely well known for her outstanding contributions in service. The number of things she does, the wisdom and the passion and the energy she brings to them is truly phenomenal. She's second to no one in the world in this. She was the president of the Society of Industrial and Applied Mathematics, which is the more applied mathematical professional society. She's received the Distinguished Service Award from SIAM, that society. And she's also received the Distinguished Service Award from the American Mathematical Society, the Pure Math professional organization. She serves on an unbelievable number of advisory boards, advising the National Research Council, the National Science Foundation, the Department of Energy, many math institutes, foreign institutions. I'm very lucky ourselves at the IMA that she agreed to serve on our board of governors and joined it a year ago, and already we're getting lots of useful help from Margaret. Margaret's also known for the passion and interest she's put into the question of helping young people, and particularly young people from groups that are traditionally not so well represented in mathematics, women, underrepresented minority groups, to think about mathematical careers. And so she's worked with students and young researchers in this. And so, in fact, she timed this coming for this lecture here so that she could participate in a conference we have tomorrow, the Blackwell Tapia Conference, which is going to be the largest gathering of underrepresented minority math science researchers ever anywhere. And Margaret's going to be a part of that. In addition, we're going to have a very interesting event tomorrow morning before the conference starts. We're going to have about 100 high school students come from around the Twin Cities area to meet some of these fabulous minority mathematicians and to meet Margaret and to learn why math is cool and what a mathematician does. And Margaret will be part of that for us, so she's doing so much for us. Finally, Margaret's very well known as a terrific lecturer. She's given all sorts of distinguished lectures. Actually, I think the latest one she's given, there's a long list, so I won't read them all, but I think the latest one she gave is probably the one she gave right here in Minnesota. She was the Cray lecturer in the computer science department just a month ago, so she's come back to us for this. We should be very grateful. And now I can sort of hear you saying, well, if she's such a great lecturer, why is this guy up there talking? Let's get her up here. And that's a point well taken, so I will give you Margaret Wright, who's going to speak to us about how hard can it be?
So, hi everybody. I hope the microphone is adjusted correctly. It's not designed well for women. It's only designed for people with pockets, so that's what this thing is in my hand. And I'm going to try to parallel process with it and the laser pointer. So here's this talk, which I'm very grateful to have been invited to give. Doug already mentioned that I wear two hats. I won't literally change hats, mathematician and computer scientist. The topics I'm going to talk about this evening actually fit into both those areas, which are not really that distinct. The benefits of careers in these areas, well, I mean, I love these fields. I could go on and on about it, but you have endlessly exciting problems to work on, and I'm going to try to talk a little bit about some of those. A disadvantage for those of you who are younger and haven't decided what to do is if you go into these fields, you get people that meet you who don't understand what you do, who ask a lot of questions that are hard to answer. Like if they find out you're a computer scientist, they say, so can you help me set up my PC? If you're a mathematician, they say, I always hated math in school, and it's sort of hard to know what to say to that. And another disadvantage is there are a lot of really bad jokes about both these fields, but there's one math joke that I kind of like, so I am now about to tell this joke, okay? It's not one of my fortes, telling jokes. So two people are in a hot air balloon. Okay, you know what those are? You're floating in the sky, they're going around, and they're sailing around, and suddenly a fog comes up. Okay, so they're sailing in the balloon and they cannot see the ground. They can't see the ground at all. They're sailing, sailing, sailing. The wind is really strong and they're really getting nervous because, you know, there are mountains in the neighborhood. So suddenly the fog lifts and they look down at the ground and they see a person standing there. Let's say it's a woman. And they call out, where are we? And the woman says, in a balloon. And then the fog closes back in and they carry on, and one of them says, she was a mathematician. The other one says, why? And they say, because what she said was perfectly correct and completely useless. I really... However, the punchline of that joke is wrong, and I hope you're convinced of that by the time I'm through this evening, because it's extraordinarily useful. If you were watching the things earlier, you would have seen why this is the case. But before I get into that, I want to explain the title of this talk. So if you Google, how hard can it be? In fact, I checked this afternoon. There were 341,000 Google hits for the phrase, how hard can it be? And this is typical. It's from the movie Thelma and Louise. Thelma says, I don't know how to fish. And Louise says, well, neither do I, but Daryl does. Daryl not being the smartest person in the world. How hard can it be? And if you look at those 341,000 entries, this is the tenor of all of them. People who think something should be simple can't believe that it's hard. And you say, how hard can it be? But in fact, you can ask the question in a serious way, and that's what I'm going to talk about tonight. So I won't be able to discuss all the ways in which mathematics can help us answer this question, but here's one. It can take a problem that looks hard and make it easy. So here's an example. This isn't really that hard, but I'm starting off slow. Okay, so if someone said to you, I have 100 numbers and I want you to add them up, you might think, oh, especially if you had to know pencil and paper or calculator. You might think this would be kind of hard, and you look at it, and so let's say we have, oops, sorry, I meant to point. So we have, this is the first number, second number, up to 100 numbers, what it is. It looks as if you need to do 99 additions. Now there's a famous story which may not be true about Gauss, who's one of the most famous mathematicians of all time. When he was 7, older I think than anyone here, younger than anyone here, his teacher wanted to fill the time in the class, and the teacher said to the students in the class, I want you to add up the numbers from 1 to 100. And to his surprise, Gauss raised his hand immediately. Well, now how did he do it? So here's how he did it. Here's 1 plus 2 plus 3 plus 4 plus 100. Well, Gauss noticed that if you took this number and this number, Put them together, that's 101. This and this, it's 101. There are 50 of those. So the answer is 50 times 101. And so it took him very little time, one addition and one multiplication. So what he did, and what mathematicians can do, is they can take a problem that looks hard and they can notice that there's something special about it, and they figure out an easy way to do it. And the great thing about what Gauss did here is, in fact, you can do this if the teacher had said add up 1 to 1,000 or 1 to 1,000,000. There's actually a formula for it. Some of you may know that, but I don't know if you could have worked it out from scratch when you were 7, the way Gauss did. But then sometimes math is very useful because it tells you that a problem really is hard. And it's important to know that. So that when you say, how hard can it be, the answer is it's hard. So there's this classic story, and I apologize if you've all heard it, but this will come in later, where there was a king, this is in the old days, who had a jester or person who played checkers with him, and the king said, "You've been such a great jester, you've entertained me, you've played checkers with me, how can I reward you?" So according to this story, the jester said, very simple, take a checkerboard, that's what we played, put 1 piece of gold on the first square, 2 pieces of gold on the second square, 4 pieces of gold on the third square, 8 pieces of gold on the next square, and so on. And the king sort of looked at that and he thought, well, how hard can this be? I mean, it's 1 and 2 and 4, it's not a big deal. Here's a checkerboard, but I think you all know the answer to this is it's very hard and very expensive. The king should have, as they say, done the math. So by the time you get to square k, the number of pieces of gold you have is 2 to the k minus 1. So on the 16th square, there'll be 32,768 pieces of gold. By the time you get to the 21st square, there are going to be 1,000,000 pieces of gold. And there are 43 squares to go. So the classic ending to this story is, well, it's either the king had the jester executed, but I prefer to think that he just had the jester banished, and he didn't give him any gold. Okay, so now I'm sorry about this, but you can't give a math talk without a few definitions, and I promise you I will only define things that we need, and I think you probably all know this. So if x is, I'll get this eventually. If x is a number and we have some constants, so we have a0, a1 up to ap, so that's p plus 1 numbers, and we form a0 plus a1 times x plus a2 times x squared, and so on. This is called a polynomial in x. Okay, so 2 plus 10x plus 6x cubed is a polynomial in x. Remember that. An algorithm is a systematic way of solving a problem. We all use algorithms every day. This word has come into common parlance. I probably don't even have to define it. Now, this is a little tougher. And again, it's used commonly, but not precisely. Exponential growth. You see this in the paper all the time, but what does exponential growth really mean? It means that it's a function of some number, and the bigger the number gets, the faster the function grows. So if you have n is the number, and you have k is some number bigger than 1, and you take k to the n, this is exponential growth. So this is just like the growth in the number of gold pieces that the jester had, because there it was 2 to the n. The fact that we need later is that if n is large enough, a polynomial in n is always smaller than an exponential function of n. It's always smaller if you take n big enough, even if this isn't true at the beginning. So here's a little example. Let's take n equal to 20, and let's take n to the 5th. And let's suppose, just to make this interesting, that doing that many operations takes 3.05 seconds. Well, then 2 to the 5th operations only takes a second. So in this case, the polynomial, the ratio, n to the 5th over 2 to the n is 3.05, and the polynomial is actually bigger. So you say, aha, the polynomial is bigger, but let's go to n equal 40. Now n to the 5th would take 1.7 minutes, and 2 to the n would take 12.1 days. And the ratio is this number times 10 to the minus 5, which means it's point, and then 4 zeros, 9.3. And if you take n equals 60, now it's 12.9 minutes, 349 centuries. And this would be true no matter what polynomial you took eventually as the number got big enough. So this will come in later. And this is the final definition for this part. So I've defined polynomial and I've defined exponential. Let's suppose we have a problem. And remember, our question is, how hard can it be? A problem is said to be in P. You should remember this because you're going to have great conversations about this later. In P, or easy, if there's a polynomial time algorithm to solve it. So what that means is there's some problem, you have some measure of the problem, and how long it takes you to solve it is a polynomial in that measure. Okay? So P means easy to solve. Easy to solve. A problem is said to be an NP if you can check that a solution is correct in polynomial time, but it seems to be very hard to solve it. And this is very important. This seems to be, and you'll see later why I say that. So NP means easy to check, hard to solve as far as we know now. It's commonly misunderstood that NP means not polynomial, but that's not the case. And some of you may have heard that in computer science, one of the famous unsolved problems is, does P equal NP? It's actually written on the sides of certain buildings because this is such a famous problem. So I'll talk about that a little more later. Okay, so we've got polynomial, we've got algorithm, we've got exponential, we have a problem is in P, we have a problem is in NP. That's a lot of definitions, but we're going to use them all. Now this is an example of an NP problem, and this is one of the best examples I know of this. A jigsaw puzzle. You have a jigsaw puzzle that has n pieces. So if someone says to you, I have put the jigsaw puzzle together correctly, it's easy to check, right? You just look at the jigsaw puzzle, you look at the pieces, and you say, this piece fits with its neighbors, this piece fits with its neighbors, and so on. So that's polynomial time. Because if there are n pieces, it's some small multiple of n. But what if the puzzle had 1,000 pieces, and you didn't know how to solve it? You might think, well, I'll do the brute force technique. I'm just going to take every possible combination of the pieces and put them together. That would be exponential. That would be very hard. So this problem is easy to check, and we think it's hard to solve. Now, I use the words brute force. Mathematicians who have a certain amount of ego always come up with ways so they look good. Okay, so if you're a mathematician, you can say, well, you can do a brute force technique, like Attila the Hun, or you can be smart, as I am, is what the implicit thing is that they're doing. And Doug already mentioned the Blackwell-Tapia conference, but here's some insightful, clever mathematicians who will be here tomorrow. Some of them may be here tonight for the Blackwell-Tapia conference. So these people are contrasted with brute force, okay, because they're very smart. Okay, I didn't put myself there. So now let's get serious. We've had two baby examples. We had Gauss, we had the checkerboard. Now let's get serious. And this is a very important example of how hard can it be. When I say very important, I mean very important scientifically, I mean very important strategically, and I mean very important if we use the crass measure of money. A security company called RSA, I'm going to get to that later, was bought in June of this year, $2.5 billion by another company. RSA was started by 3 mathematicians who thought of a very smart thing, which I'm going to tell you about later. So it's serious. I won't promise you that every one of you who goes into math is going to make $2.5 billion, but it's worth thinking about. So cryptography is in the news a lot, and it can be defined in different ways. And this is a very simplistic definition, but it's communicating secrets securely. This problem has been around for centuries, for thousands of years, and it started in military contexts. So a famous cipher is named after Julius Caesar, who was the Roman emperor who lived from 100 to 44 BC. And here's a quote about what he did. Basically, if he had anything confidential to say, he took the alphabet and shifted it by some number of letters. And so then when he met A, he put D, and so on and so forth. And so this is the word that would come out if you use this to be cryptography. So if you were trying to do cryptography, you would take C, you would take the 4th letter after that, which would be F, and so on and so forth, and obviously wrap it around. So that's the Caesar cipher. And of course, this was helped by the fact that in those days, hardly anyone knew how to read and write. So he didn't have to worry about his communications falling into the hands of too many people. Okay, a more complicated version of this that I'm sure you've heard about, and I could have given this whole talk on cryptography, it's really fascinating. Instead of just doing take the alphabet in order and shift it, you do something more complicated. So you say like A goes to D, and F goes to Z, and so on. So you have a substitution. This is a very simple example where we've just pasted zebras at the front of the alphabet. So this is harder to figure out, right, because you don't know what the substitution was, but if you wanted to say flee at once, it becomes this. Now the way this is cracked, and if you read mysteries as I do, you know that when they crack this code, they always do a frequency analysis. So they say in English, the letter E is the most common letter, so we think that, E corresponds to something else. Another way this crops up in mysteries is that there's a secret book on a dusty shelf, and in that book, on some page, someone has circled the letters, and that's how you find out what the code is. Now, this is only the beginning, and I'm not going to go into all the other possibilities, but I have to introduce this crypto. By the way, if you're really cool, you say crypto, not cryptography, so I want you all to do that tomorrow, talk about crypto. Encryption is to take some data, like a message, like the secret location of the oil fields, and you transform it into a form you hope cannot be read by people that you don't want to read it. Decryption is the opposite. You take an encrypted message and you convert it into something you can read. And what do you use to do encryption and decryption? You use a key, which is information that allows that. So in the Caesar example, it would just be the shifted alphabet. In the other one, it would be whatever the transformation was. Okay, now this is an extremely important point, and I'm sorry to point it out explicitly, but I want you to know this. For thousands of years, okay, a lot of mathematics has been done for thousands of years. The best minds thought that the only way to communicate things secretly and securely was to have a secret key. It makes sense, doesn't it? I mean, if I want to communicate something to you in some way, and I want you to be able to get it and no one else, we need to know a secret. And so there's a big problem today. I mean, it certainly was a problem in the past where things would fall into the hands of the enemy. The secret book would fall into the hands of the enemy. The Enigma machine in World War II would fall into the hands of someone else. But how these days with the internet do you communicate things securely? For example, I hope none of you send your passwords by email. That's not very secure. So if you're trying to tell someone what your password is, you're basically blowing it completely if you do that. Now, in 1976, a while ago for some of you, but not for everybody, that's the year I got my PhD, there was this incredible breakthrough. Incredible. People could not believe that this could happen. Diffie and Hellman, so this is Diffie, this is Hellman, and a person named Merkle. These two were at Stanford and he was at Berkeley. The idea there is use a public key. Okay, now that seems really startling and people couldn't believe that it was the case. And if you ever read the history of this, it's fascinating. The National Security Agency, people came to Stanford and sort of stood threateningly in the halls because they were worried that this was going to, ruin national security and so on. And you think, how can this be done? How can we communicate securely secrets with a public key? And the answer is you use math. Of course, that's the answer. And the RSA public key algorithm was invented the next year. Diffie and Hellman proposed an algorithm which these people here, so this is Shamir, this is Rivest, and this is Edelman, and they were quite young when they did this. They came up with the RSA public key algorithm. It's Rivest, Shamir, Edelman, and if you want a great website, you should go to this website of the company that I said was bought for $2.5 billion. Okay, so here's how it works. Every person has a pair of keys. Okay, so you're a person and you want to send some secrets. You have two keys. One key is public. And you publish this key and you say, this is my key. And then you have a private key and you're the only person that knows it. You don't have to tell anybody else what your secret key is. It's your secret key. In fact, you shouldn't tell anybody else what your secret key is. So notice, 2 people don't have to know a secret key anymore. Only 1 person has to know a secret key. And before I go into this, I just love this part. So in the RSA paper, they introduced the 2 most famous characters in cryptography, who appear everywhere in all discussions of cryptography in any language all over the world. Go to any website about cryptography and you will find these 2 characters, Alice and Bob. Now this is because they didn't want to do the boring math stuff of take A and B who want to communicate. They actually gave them personalities. Alice and Bob want to communicate. So here are just a couple of the things I found on the web of Alice and Bob. Alice, you're the one for me, but Bob, how can we be sure? I don't know Italian. Some of you do. Someone told me this means, how can I tell Bob I love him? And this says, I wish I could get that letter from Alice. So Japan, China, Egypt, all over the world, Alice and Bob. And there's another cast of characters too, but I think this is great, instead of A and B, which would have been really boring. Okay, so here's how Alice sends a secret to Bob. She looks up his public key. Remember, he's published his key. She uses it to encrypt her message to him, and I'm going to show you how to do that in a second. Bob is the only person that can decrypt it. He's got a secret key. He's the only person that can decrypt this message. And then Alice doesn't know his secret key. She only knows his public key. And then he does the same thing if he wants to send her a secret answer. There's another character that's sometimes around called Eve, which means an evil eavesdropper, who knows that they're communicating, but Eve cannot tell what the secrets are that they're doing. It's so great. Okay. This is another definition, which again, probably you know. It's called modulus arithmetic. So when you write A mod B, where these are integers, it gives the remainder when A is divided by B. Okay, so 21 mod 5 is 1 because 21 equals 5 times 4 plus 1, so there's 1 left over. 42 mod 8, the same. Okay, this is probably something that you know, but we have to have this for the next example. So here's how RSA works, and I'm not going to go through this in any detail. You can find this on the web. Okay, so you pick 2 prime numbers that are about the same size. You know what prime numbers are, right? They have no factors except themselves and 1. Then you multiply them together, and you take each one and subtract 1 and multiply that together. So you have this number n, which is the product, and this number m, which is the product of p minus 1 times q minus 1. Then you pick a number e so that e and m have no factors in common. So it would be like 2 and 7 have no factors in common. And then you compute a number d so that e times d is 1 mod m. That's this number. So I explain what modulus is, and I don't expect you to follow this. So Bob's public key is the pair en, and his private key is d. So now we have Alice. She wants to send Bob the message m. She knows what e and n are, so she computes this number cm to the e mod n. So this is just a computation that Alice can do. It's not very hard. And then when Bob gets that message, c, he decrypts it by computing m equals c to the d mod n. And remember, now he's using his private key. So Alice only uses the public key to encrypt. He uses d to decrypt. Now, what would be the situation if someone wanted to read that message that wasn't Bob? They would have to know D, right? They would have to know D because this is how he figures it out. Okay, now to compute D, here's how we got D up here. You have to have M, and that means you need P minus 1 and Q minus 1, and that means you need P and Q, which are the factors of N. Remember, that's the public key. So if you want to decrypt and you don't know D, you have to factor N. So here's a simple example. So let's take P equals 11, Q equals 3, N is 11 times 3. Now this is a terrible choice because all of you can look at this immediately and say, well, I know what the prime factors are. They're 11 and 3, but this is just a simple example. So M is 20. Now you choose E equals 3, which doesn't have any common factors with 20. You choose D equals 7, and here it's worked out. So your public key is E and N, 3 and 33. The private key is 7. This is the simplest possible example of RSA. So if Alice wanted to send the message m equals 6, which might mean I love you, or let's meet tonight at 6 p.m., or whatever, I've broken up with you, I don't know what Alice is sending. Here's what she would do. She would compute c equals m to the e mod n, so 6 cubed modulo 33, which is this computation, which is 18. So she sends the message 18 to Bob. And now he's going to decrypt it. Okay, so he's using his private key. So it's c to the d mod n, 18 to the 7 mod 33. Whoops, 18 to the 7 is kind of a big number here. But you can compute these things using math, of course, and so you get 6. And that's the message that Alice had sent. And we don't know if he's happy or sad, but he got the message. So how can this be secure? I hear you cry. We have this number, and we need to get its prime factors. How hard can that be? You think to yourself, this is what people thought before Diffie and Hillman, factoring is sort of like the opposite of multiplying, right? You multiply two numbers, or you factor into prime factors. Probably you do this in school. Now, it's very interesting. Multiplying two n-digit numbers using what you learned in grade school is polynomial, right? Takes n squared steps. That's a polynomial. So that's easy. And if someone says to you, these are the factors of that number, you can check that by multiplying them out, right? So that's easy. Remember, NP means easy to check. But it's very hard, as far as we know, to factor. So the best algorithm today for an m-digit number to factor it into primes is exponential in the square root of m. So factoring is an NP. It's easy to check, and it seems to be hard to solve. So now let's talk about some practical considerations. If n is not large enough, then we have people who are attacking the system, right? Anytime you have a cryptographic system, they're hackers that do it for fun. They're nasty people that want to break into your system. Maybe there's a jealous girlfriend, a Bob, who doesn't want Alice to send him any messages. Who knows? And you can do brute force. So you can take the number and you can just try the prime factors, okay? Brute force. And how is this possible? It's possible because computing power is so good today. In 1976, when this started, the fastest computer could perform 1 million operations a second. Today, the fastest computers available to the public, and I say that because it's pretty widely believed that the National Security Agency and other agencies like that have faster computers that we don't know about. So these are the fastest ones that are available to the public. They can get hundreds of teraflops. That's 10 to the 12th operations a second. So that's 1 million times faster than it was in 1976. Now, you might say, well, 1 million, big deal. For perspective, keep in mind that a jet plane is only 40 times faster than a human running at top speed. Think of trying to run across the United States, if you could do it at top speed, and how long that would take compared to flying in a jet plane. I mean, you wouldn't even consider running across the country, would you? But this is only 40 times faster. Think of 1 million times faster. Think of being able to cross the country in much less than 1 second. That's what we're talking about. So a brute force attack with lots of fast computers could easily factor in. You wouldn't have to be smart at all. You would just use brute force. Attila the Hun, you wouldn't need mathematics. So now I'm expecting all of you to want to do this. RSA has this great thing called the Rsa Factoring Challenge. Rsa Security, the company I mentioned that was bought for $2 billion, puts huge numbers on the web and challenges people to factor them. And it pays you if you factor them. Okay, so this is a 193-digit number. RSA 640, here it is. Probably you can't factor that in your head. And it was factored about a year ago. It took about 5 months of calendar time and about 30 years of CPU time. So all these computers were running to factor this number. And here are the factors. And you can multiply them together in n squared time to see if they're equal to n. You say, well, that's not very interesting. It's been factored. Okay, so this is RSA 2048. There's $200,000 if you factor this number. Okay, so I'm expecting those of you who have nothing better to do and who think math isn't very useful Get with it and factor this number, okay? And you'll win $200,000, and you'll be mentioned on the RSA website, and the National Security Agency will probably come to visit you. And you don't have to write this down. You can find it on their website. Okay. So let's get back to the, have you got it written down? So let's remember, the question is, how hard can it be? How hard RSA is, how hard factoring is, we don't know. We do not know. And if you look at the RSA website, they keep saying, we do not know how hard factoring is. Experts are convinced that factoring is hard. There's 30 years of experience, but it has not been proved mathematically. Now, I don't want you all to go to bed tonight and worry about this, because the National Security Agency and other people like that think about this a lot. Okay, but it's good for you to know about this so you can have an intelligent opinion about cryptography, and tomorrow you can all talk about crypto and Alice and Bob and the RSA Security Challenge and work on that $200,000. Okay, so I have one more topic, which is called linear programming. It's a different spin on how hard can it be. George Dantzig, here he is. He died last year, affectionately known as GBD. He's one of the people I worked with at Stanford. He's the father of linear programming. Linear programming is a business worth hundreds of billions of dollars. If you look on the web, you will find linear programming used in just about every application of business. It's worth so much money, you cannot even begin to estimate how important linear programming is. So it's an interesting mathematical topic, it's a fascinating topic to work on, it's also worth a lot of money. So I guess for those of you who might be thinking about math as a career and maybe don't think you can make any money, wrong, you can. Okay, so linear programming is a modern field of mathematics. It's about 60 years old. It dates from the end of World War II. And in those days, programming did not mean what it means today, because we didn't have modern computers then. It meant developing a plan or an organization or schedule. Okay, so people would talk about programming, and what they meant is, let's figure out how to organize this, let's figure out how to schedule things. So what is linear programming? Now, I don't like to do this, but I'm going to use definition by example. I don't know if in your math classes you've ever had proof by intimidation. Your teacher just says, this is true and you'd better believe it, and I say so, and that's that. Proof by intimidation. Definition by example is not quite as bad, but it's not great. So a linear function, if we have 2x is a linear function of x and x squared is nonlinear. 2x plus 3y is a linear function of x and y. 2x plus y squared is a nonlinear function. So there's linear and there's everything else, okay? So in 2 dimensions, okay, so now this is x, this is y. The contours of a linear function, meaning the lines along which the function has the same value, are straight lines. So this line here means that some linear function has the same value. Has the same value here, it has the same value here, it has the same value here. You get the idea. The color code here is red is big, blue is small. So the linear function is bigger up here and smaller down there. Okay? What about a linear constraint? I'm going to do another definition by example. So we've had a linear function. What a linear constraint is, it says take some linear function. Let's take this blue one here. And I want a point to be either on this line, or on this side of this line, or on this side of this line. Okay, same with this green one. I want a point to be either on this line, that's called a linear equality constraint, or here, which is on this side of it, or here, inequality. So this is 3 linear constraints. And if you wanted to be on this side of the blue, that side of the red, and that side of the green, it would be this little triangle here. Okay, so what's linear programming? Linear programming is optimizing, that means finding the biggest or smallest value of a linear function subject to linear constraints. So if we take the contour lines we had before, and we take the constraints we had before, and we say, where is this function that is plotted here the smallest? You can see it's right there. Okay, so remember, red is big, blue is small. If you go any farther, you're outside the region where the constraints are forcing you to stay. So that's linear programming. Okay, my abstract said that eating a good breakfast was easy for most of us. And you might think, how does this have any relationship to linear programming? So the first application of linear programming, and one of the stories that George Dantzig loved to tell, and I love it, and I'm going to tell you later, was about how to feed the troops a nutritionally adequate diet at minimal cost. So the military were very worried about this. They had a lot of people that were in the Army, in the Air Force, and the Navy. They all had to be fed. They wanted to feed them a nutritionally adequate diet, but they wanted it to be as cheap as possible. Okay, so these are called diet problems, and they're very famous. So we have a choice of foods, and we want a minimum cost diet that satisfies nutritional constraints. Now, suppose that I didn't put any nutritional constraints, then obviously the cheapest diet would be to eat nothing, right? You wouldn't eat anything that would cost nothing. So that's clearly not the way we're going to get the right answer. So I just made up this example for this talk. So suppose we have some foods to choose from, 8. And we want not just a good breakfast, but an optimal breakfast. So we have pancakes, milk, freshly squeezed orange juice, scrambled eggs, Weetabix, which is a high-fiber cereal, fresh blueberries, bacon, and vitamin and mineral pills. Okay, here they are. You can't imagine how much fun I had looking on the web to find these pictures. These are the best pictures of bacon, pancakes, etc. So these are the foods you had to choose from, and picture yourself at a buffet where you're trying to choose among these foods. Okay, so what our goal is to find the cheapest diet where we get enough fiber and we get enough calcium. And of course, the x's have to all be non-negative because you can't eat -5 amount of blueberries. So here's pancakes. It has 5 units of fiber, 10 units of calcium, and it costs 3. I haven't said what. Weetabix has 100 units of fiber, 20 units of calcium, but it's kind of expensive. It costs 10. Blueberries have a lot of fiber, quite a bit of calcium, and they're not very expensive. Bacon, I'm sorry to say, has no fiber, no calcium, and is kind of expensive. The pills, on the other hand, have a lot of calcium, and they're pretty cheap. So if we formulate this as a linear program, we write down the cost, we write down those constraints, this is what we get. Okay? This is breakfast. 1.14 units of Weetabix, 0.19 units of vitamin and mineral pills. Not even any milk for the Weetabix. This is the optimal breakfast. And I think yuck is the correct word here. Okay, so what's the original story? This is a version of George Dantzig's story, and his story is true. So remember, this is in World War II. They're trying to feed the troops. They're using linear programming for the first time, and it was solved by computers, and in those days, computers were people that sat there using calculating machines. So if you read old stuff about computers, it's a room full of people. Okay, and it took days to solve this problem. Days and days and days. And the answer came out, 20 beef bouillon cubes and 20 vitamin pills. Okay, so now imagine going to the general and saying, General, we've found the best diet for the troops, and it's 20 beef bouillon cubes and 10 vitamin pills. Well, people were not too happy about it, and they thought it had gotten the wrong answer, and there was weeks and weeks of effort, and it was a terrible answer. But it was the right answer. It was not the wrong answer. It was the right answer to the problem that had been given. Okay, it was something that was wrong was the problem formulation. It needed more constraints. Obviously, whatever constraints they had did not constrain it enough. Okay, so here's the message about how hard can it be. Math can tell us a lot, but it can't always tell that it's been given the wrong problem. This is a very important truth that you will need to know if you work with people on real-world problems, because often they come to you and they say, this is my problem. And you say, well, this is the answer. And they say, are you crazy? That's a terrible answer. And you say, well, look, I can prove that it's optimal. And then they'll say, oh, yeah, I forgot to tell you this one thing, or this other thing. So math analysis can sometimes tell you that it's not going to be what you think. So in the breakfast problem, because of the nature of a solution to a linear program, which I'm about to describe in a minute, you would actually know in advance that the optimal breakfast would only have 2 foods. They could have figured that out in World War II if they'd thought about it. And so really you would think, 2 foods, that's probably not going to be a very good breakfast. So what's the lesson about hardness? The hardest part can be getting the problem right. You know, the problems are not handed down from on high. The problems are formulated by people, and they don't always get them right. But now I told you what linear programs were, and I solved one for you. How would you solve them? So this is what I'm calling proof by picture. Okay, here's our picture again, and we want to find the lowest value of this function inside this little triangle. Well, it's pretty obvious that functions getting smaller as you go down, that the very best value is right here, right? That's obvious. You can't go any farther without violating the constraints, and if you're higher up, you could actually move down. So the optimal solution, essentially always, and I say that because I'm a mathematician and have to be precise, is at a vertex, meaning a corner point. So in any dimension, you can have a vertex. And it's always at a vertex. And that's how you would know in the breakfast problem that there would only be 2 foods, because a vertex would have 2 foods in it. Okay, so what did Danzig do? He invented the Simplex Method, which is a brilliant method. It's been called one of the top 10 algorithms of the 20th century. It's worth billions and billions of dollars. He never got a dime out of it, by the way, because he put it in the public domain, in contrast to RSA, who wisely got a patent for their algorithm. But George came up with this thing by saying, we know the solution's at a vertex. We start at a vertex, and then we sit here and we see if we can get a smaller value of the objective. And you can see if you start here, you can move down to here, and then you move to this vertex. And then you say again, can I get a smaller value of the objective? The answer is yes. Move over to here, and when you get to here, you say, can I get a smaller value of the objective? And you can't, so you're done. So that's the optimum, and that's the Simplex method. So how hard can it be to solve an LP with the Simplex method? Well, it's kind of worrying here. I need to tell you that if you have a linear program in n variables, you can have an exponential number of vertices. So could it be the case that you would actually have to visit every single one of those vertices? That would be a bad algorithm. That would mean it would take a really long time to solve. But this history is fascinating. So for the first 25 years after the Simplex method was invented, people jumped on it and they used it to solve linear programs, and they were happy. They were really happy. They solved their linear programs, they did use them in their company, and they didn't really worry about this. And why were they happy? Because in practice, the Simplex method, I described moving vertex to vertex, almost always took 2 to n to 3n steps where you had n variables, and each step took about n squared. So that would be an n cubed algorithm. It's polynomial. So in practice, the Simplex method was extremely fast. It was polynomial time, and people said, great, it's solving our problems. But from a mathematical perspective, this meant nothing, okay? I have to tell you another thing which I think is a great property of mathematicians, but many people hate, is that they can find nasty problems that make something that you thought of that's really clever perform badly. It's just like the great thing where you have something and you think it's true and someone says, but here's a counterexample. Well, if you're in math, you just say, well, that's it. Okay, there's a counterexample. It's not true. Other people don't like that. I once had a big argument with someone who kept saying, that's just one example. And I said, yeah, but you said this was always true. He said, but that's just one example where it isn't true. I said, oh, okay. Not a mathematician, let me add. So if people don't like it, but some people do. And it's something, if you have that kind of mind, math is the career for you. Okay, so Klee and Minty in 1972 produced a linear program that has n variables, and it has 2 to the n vertices, and if you start the Simplex method at the wrong vertex, it will visit every one of them. 2 to the n, exponential, not good. And here's Klee Minty in 2 dimensions. Okay, so it's got 1, 2, 3, 4 vertices. You want to be inside this triangle. And you want to minimize the linear function, which is getting smaller as you go there. And if you start at this vertex, it goes, let's see, 1, 2, 3, 4. That's 2 to the n. And you might say, well, whoop-de-doo. As the king said, to the jester. How hard can it be? But of course, this is a 2D example, and we all know that 2D is meaningless when you're talking about exponential. So that was that. Clementi showed that the simplex method could be exponential time. And there was this interesting anomaly that LPs seemed to be easy to solve. In practice, they only took a linear number of iterations, but there was an example where they took an exponential number. So for years and years and years, people thought about, could there be a polynomial time algorithm for linear programming? And I'm going to go through this too fast, but I don't want to run over time. I'm happy to talk to you later. So in 1979, a 28-year-old mathematician working in the Soviet Union actually defined a polynomial time algorithm for linear programming. This was an amazing thing. The simplex method had been around since 1947, and no one had thought of a polynomial time algorithm for linear programming. Kachin did. Because he was in the Soviet Union and because the US was not on good terms with the Soviet Union at that time, this did not make the US military very happy because they thought, based on what I told you earlier, remember polynomial time is always smaller if the number is big enough, remember that? They thought, oh no, they're going to be able to decrypt and they were very confused. They thought cryptography had something to do with linear programming. But in practice, Kachin's algorithm turned out to be much slower than the simplex method. In 1984, Narendra Karmakar, also 28, I don't know what it was that was magic about 28, but anyway, he came up with a polynomial time LP method that he said was 50 times faster than the simplex method. It turned out that that algorithm was formally equivalent to an earlier class of methods, and people got very interested in it because this was a polynomial time algorithm that was faster than the simplex method, at least according to his results. But there's an anomaly that's been around for 20 years. So this is my area of research, which I will mention just briefly. So 84, this thing came out. And interior point methods for LP, which is what these polynomial time ones are called, can be much slower than simplex still, even now, on problems that are huge, that have tens or hundreds of millions of variables. How can this be? Remember, I said polynomial has got to be smaller than exponential. So something else is going on. Maybe there's special structure in these linear programs. Think of Gauss. And there's very recent theoretical work by Spielman and Tang that shows the simplex method is polynomial time in the average case, but it performs much better than their analysis shows. So there's still a mystery. And my abstract said math can tell us a lot, but it can't tell us everything. And here we don't have all the answers. Okay, so let me just summarize. In cryptography, the most popular system in public key cryptography rests on the fact that factoring is hard. EMC did not pay $2 billion for RSA because it thought it was going to be easy to break RSA crypto. So there's every reason to believe it, and cryptographic systems have flourished, I put as far as we know, because we never know what the NSA is really doing about this. But anyway, as far as we know, but no one's proved that factoring is hard. No one has proved that these other NP hard problems are actually hard. It's wide open. You would love it. You should work on it. It's great stuff. And real-world cryptography, I have to tell you, is way more complicated than what I talked about here. I mean, we have all kinds of attacks and different things. I just want to make a simple comment here. Guessing people's passwords is not cryptography. There are about 200,000 words in English that are 8 characters long. With modern computers, you could try every one of those in less than a second. Okay, so if your password is an English word that's 8 characters long, forget it. Someone could crack it in a second. If you put numbers in and you mix it up, it's going to multiply it by a few factors. It might be a few trillion combinations, 5 seconds on modern computers. So passwords that are simple and that are based on using things like English words are trivial to crack. Okay, that's why your systems administrators always say, don't have your password be too simple. And for most of us, let me just add, nasty people with a lot of computers are not trying to break our passwords. That's what keeps us safe. It's not that they couldn't be broken, it's that no one is interested. And your friends probably don't have enough compute power to crack your password. At least let's hope not. Okay, linear programming. Today, faster computers and algorithmic improvements mean you can solve enormous linear programs very quickly. Airlines routinely solve linear programs with hundreds of millions of variables all the time. But we do not know why the simplex method is sometimes better and sometimes worse than a polynomial time method. The theory would suggest that this cannot happen, and yet it happens all the time. And why are both of them more efficient than the analysis shows? I didn't go into this in detail, but for most problems, they run much faster than the complexity shows. So math has told us a lot, but not everything. Okay. In both of these cases, and remember these are billion-dollar industries, you can do things much better if the problems have special structure. And a huge number of linear programs have special structure. A lot of cryptography problems have special structure. Think of Gauss. So if you come up with a way to deal with a special problem, you can make it solve much faster. So there are just these great insights. I've only sketched a few of them where we look at how problems are hard, we think they're hard, we don't know they're hard, sometimes we know they're hard, sometimes we know they're easy. And for all of us who are in math and computer science, I can't tell you how lucky we are to have so many problems to work on while we try to figure out how hard can it be. Okay. And I just want to thank Google and Google Images, without whom this talk could not have happened, RSA Labs website, Wikipedia, and Ian Stewart for the Jigsaw Puzzle, which I think is the best example I know of a P and NP problem. Thank you.
Let's see. We have time for a couple of questions. First, I want to check, has anybody factored the number? Okay, I was going to talk to you about donations to the IMA.
Give that man $200,000.
There's a question here?
Yes.
Will quantum computing change all this or any of this?
I'm sorry?
Will quantum computing change any of this?
The question is, will quantum computing change any of this?
Okay, so that's, of course, interesting because the Alice and Bob thing I showed, where Alice said, in a quantum world, how can I be sure? If you believe we're going to get practical quantum computers, and I'm not going to attempt to define that, then there would be a polynomial time algorithm for factoring, which means all the RSA, factoring is hard stuff would fall away. However, no one has yet built a practical quantum computer, but I can assure you that people are worried about this, and RSA and other companies like that are paying a lot of attention to it. So it would change it. The one thing I want to say is, remember that Kachin's algorithm was polynomial time, and it's pretty much always slower than the simplex method. Not for Klemente. And so no one knows if the polynomial time factoring algorithm from quantum computing would actually be faster than some of these other techniques. Would it be fast enough to keep ahead of the RSA challenge? And we just don't know. That's a very interesting research topic.
One more question? Joseph.
So there's a lot of conjectures on where prime numbers are situated on the real line. For example, the twin prime conjecture about primes being two numbers apart. Are any of these conjectures, would solutions to any of these conjectures help out in factoring prime numbers? Are there any conjectures that are related to this problem?
Right. So again, I couldn't go into this in detail, but if you look at websites about this, they explain how all these results in number theory would have an effect on this. Okay, so in the RSA thing, I said pick P and Q large prime numbers. If you don't pick them carefully, there's actually an easy brute force attack, that will just find them. And so there are all kinds of interesting subtleties which involve special structure in the problem. And if you don't know enough math and number theory, you can think, oh goody, I've got this great thing, and it can just be broken instantly. So, I mean, I have to say one of the great things that I think has happened is that number theory used to be seen as one of the purest of the pure areas of math that had no use whatsoever. It was like the balloon thing. It's essential. I mean, without number theory, none of this cryptographic stuff would work. So I should mention there are other things to do to keep secure. So there's elliptic curve theory. There's some cryptography systems that are based on elliptic curves. There are other things that are not based on factoring. And people believe they're hard too, but it's the same. They're easy to check. They don't know if they're really hard or not. I mean, I think it's a fascinating area. So either one of these problems, if you figured out something special and new, you would be a great hero in math and in the real world, and you could win a prize, and you could start a company, and you'd also have a lot of fun.
I should mention that a group of algebraic geometers from around the world will be coming to the IMA this spring to talk about cryptography and applications there. Okay, let's thank Margaret again. And I just want to mention before you go, we have a few things up here. We have the poster for the whole lecture series, if you'd like. The next talk is going to be on January 18th, Making Sense of a Complex World. And if any students need certificates of attendance, we have those as well. Thank you and good night.